So here we are, we're gonna talk about principal component analysis. So PCA, so principal component analysis, is basically we have a data set, and this data set exists in the vector space from linear algebra, and we are going to transfer this data set from this vectorial space to another one, and we're gonna choose the basis for this new vector space. And we want to choose the basis for this new vector space so that it's gonna make learning easiest for our machine learning models. In order to do that, you should know that the most variance, more predictability the data is going to contain. So we are going to choose our new basis so that each vector of the basis is going to contain the most variance possible, so that we're going to lose so it's going to contain most information for each vector of this space. So what is PCA? It's just a linear transformation in the data. It's just a kernel and perform a linear transformation in the data, and no big deal. So what's the purpose of it? You can use it in a constant number of dimensions. Here's a very simple example with synthetic data, just to show that you have this data, and because it's everything mostly applied to a same line here, it's when you're gonna perform some form of learning here, supposing you had different classes or clustering, you are gonna have a lot of useless information here, so all the data is concentrated in this way. So after PCA application, you see the data is more evenly spread across the data set. Here is during the process, and so you choose a different basis and perform this linear transformation here. And it can also be used for dimension reduction. You can have more dimensions and transform it. We have an example here with a data set. We're going to transform it from 4 dimensions to only 3, so it's easier to plot. And so that you can remember, if you decrease the number of dimensions, the number of features of a class, of your data, you can learn a lot faster. You can use a smaller model, so easier to train, faster, and needs less memory. It's a lot more efficient this way. Now, how are we going to do principal component analysis? Here's just important data. First step, centralize and rescale the data, as we do in every single machine learning problem. Then compute the covariance matrix. So what is the covariance matrix? The covariance matrix is a matrix that shows all the covariance between each features. So the first line and first row is the variance of the first feature. First column, second row is the covariance between the first feature and the second feature. First line, third row is the covariance between the first feature and the third feature, and so on. So it's just like all the covariances between all the features. So each ji is simply the covariance between feature A, feature J, and feature I. So and it's gonna have the shape, dimension, or the number of features per number of features. That's the dimension of the covariance matrix. So step number 2, very simple. Compute covariance matrix. Here's very simple formula to calculate it. And compute the eigenvectors, eigenvalues of the covariance matrix. Now, how amazing is this? Each eigenvector of the covariant matrix is our principal component. Very big coincidence. So, the covariance matrix is gonna choose each one of our principal components. And our eigenvalues, which is associated, each eigenvalue associated with one eigenvector, the eigenvalues show us which are the representativeness of the variance of that eigenvector. So the bigger is the eigenvalue, more variance that eigenvector contains. So here are our eigenvectors. As we are doing this to choose those vectors who have the biggest representation of the data, we are gonna pick the ones that have the biggest eigenvalues. And we're gonna choose how many we want. We can keep all of them. We can have only one, only two. In this case, I would say we can have only two because they contain most of the variance here. We would lose very little information by dismissing, because see, this one is more than 100 times bigger than this one, so we would lose very little information by discarding the last eigenvalue. And the principal component is not one axis, is not a feature, is simply a linear combination of each feature, so a proportion of each one of these features, okay? Don't confuse. Then and last step is a space transformation. We're gonna take each one of the data points of our data and transform to this new vector space, where the basis of this new vector space is each one of the components that we just found out here through the eigenvalues and eigenvectors, using as many as we choose. Now, here's the complete code from scratch, and we can use NumPy to calculate it for us. Now we are gonna make a few examples here. Go for a few examples. Here's just some. Here, this data is the iris data set from UCI. I'm importing here. Here is feature 1 versus feature 2, feature 3 versus feature 4. We can't really see much because it's 4 features. And as we just showed here, the first feature contains most of the variance. So we could discard at least one and maybe even 2 of them. Here, the first one contains most of the variance, so we can discard 1 or 2 of this and keep only the first 2 and do all our machine learning in only those 2 features. Here's the data before PCA in 3 dimensions. Now, here is the data after applying our algorithm. The first 2 features, it was too many features, so we can't really compare, but you see, you can kind of separate this very easily with one, or like one here and one here, two lines here. You could classify this data so easy. And here is in 3 dimensions, how you would classify. So it's kind of easy to classify, but yeah, but here we only lost 1 dimension. Here, second example, wine data set, which is also a classic model. And here's the original data, the first 2 features, but the thing is, this data have 13 features. So plotting the first 2 features, it's not like we are seeing much. But you see here, after we apply principal component analysis, it's almost as if only one axis here is representing everything. So almost like you could have only one axis, and then here is principal component with only two features. But it doesn't look very different, but yeah, we can see it makes kind of a difference here. And the explaining variance ratio, the first one contains more than 99%. The others are kind of always the same. And I would say we could reduce this model here to use only two features, because you see we have only the first four have a positive and the others are like negligible. So instead of having 13 features, we could have only 4. So a lot easier to train. Here's the data before PCA and after. So you don't see that much of a difference, but it's because it has too many features. You have 13. And here is MNIST, also a very classic example. Big data set, 784 features. We can, and here I plotted a bar plot of all the explained variance of each of the principal components, and we could take only 200, only 150 or 200, and have 99% of the variance here. So see, you can reduce the number of features to only 20%. The features you had usually 20 or 30%. So dramatic reduction, faster and efficient. That's what PCR is for. And the idea is simply like transforming from one space to the other space.